In this video, we'll go over dipole antennas. All these antennas here are dipole antennas. Now, this is a 5.8 gigahertz antenna. This is a 5.8 gigahertz antenna. This is a 2.4 gigahertz antenna. And this is a 433 megahertz antenna. So what you notice is that as the frequency gets lower, the antennas get bigger. The most common dipole antennas you see are about half wavelength long, consisting of two quarter wavelength sections configured like this. Another common type of dipole is called a sleeve dipole and is constructed with a coax cable with quarter wavelength of the center conductor sticking out and a conductive sleeve soldered to the outer conductor and folded back over the coax. To make this antenna, I just took the monopole antenna from the last video and soldered a copper wire onto the outer conductor and trimmed it to about quarter wavelength. So you see at 5.8 gigahertz this antenna has an SWR of about 1.1, which is a pretty good match. The problem with a dipole center fed with a coax cable is that we end up with coupling from the antenna to the feed line that negatively affects our radiation pattern. One way to reduce this coupling is to use a type of balun called a sleeve balun, and it's basically just a ferrite bead placed near the feed point of the antenna. Ham radio operators constructing large antennas on their property will often feed dipole antennas with a balanced transmission line called ladder line to further reduce this coupling. This 433 megahertz dipole antenna is already a pretty good match, but here you can see by trimming it just a bit we can improve the SWR from about 1.4 to about 1.3, which only equates to a 1% increase in efficiency. Now let's talk about a topic a lot of people have trouble with: antenna gain. Gain when referring to an antenna does not mean amplification like with an op-amp. Antenna gain is a product of the antenna efficiency and the directionality of the antenna. When looking at antenna specifications, the gain is often listed as dBi, and the I is referring to a hypothetical isotropic antenna that has a gain of 0 dBi, which means that it radiates in all directions equally. If not specified, the listed antenna gain is the max gain of the antenna. A good way to visualize antenna gain is with the stick of putty. The maximum size of the stick is dependent on the power of the transmitter and the efficiency of the antenna. The small piece I just cut off represents the power losses. Now let's say we have three antennas with the same efficiency connected to the same 100-watt transmitter, but each have different radiation patterns. The volume of putty for each antenna is the same. The first pattern represents a half wavelength dipole and is pretty omnidirectional. The middle antenna radiates most of its energy in two directions and has a higher max gain than the dipole. The antenna on the right has the largest max gain of these three antennas, so it can reach the farthest distance, but only in one direction. If you want to reach longer distances, you'll either have to increase the antenna's efficiency or increase the power of the transmitter. This is how a single dipole radiates when viewed from above. To increase the gain of a dipole, we can place an identical dipole antenna parallel to the first, 1/2 wavelength apart from each other. When powered in phase, we get cancellation in line with the antennas and gain in the direction perpendicular to them. When powered 180 degrees out of phase, we see the opposite occur. When the dipole antennas are not placed 1/2 wavelength apart or the frequency increases, we end up with unwelcome radiation patterns. Hope you guys liked the video, and I'll see you next time. Today we're going to take a look at monopole antennas. Okay, so monopole antenna is basically just an antenna with a single conductor like a pole. So all of these antennas here are monopole antennas except for this one. So I just wanted to show you that just because it looks like a monopole antenna doesn't mean it is. So this one is actually a dipole antenna. So we have our monopole here and then the other half coming back down over the shield there. For a monopole antenna, the most common length is a quarter wavelength. To calculate the wavelength, we use the equation lambda equals V over F, where lambda is the wavelength, V is the speed of light in a vacuum, and F is the frequency. V is equal to 300,000 kilometers per second, or 300 million meters per second. So lambda equals 300 million meters per second, all over 5.8 billion cycles per second. So let's just take the units down and see how they cancel out, and we're left with meters. So lambda equals 51.7 millimeters, or 2.035 inches. So quarter wavelength would be 12.9 millimeters, or 0.509 inches. When designing a quarter wavelength monopole antenna, it's a good idea to just start out with a longer conductor than you need and then trim it down to tune it to frequency. Now let's take a look at these two quarter wavelength monopole antennas that I trimmed down for the best SWR. So taking a look at the graph, we can see that the antenna has an SWR of about 1.33, and taking a look at the Smith chart, we can see that everything across the center line here is a resonant frequency of the antenna. Everything in the top has a net inductive reactance, and everything in the bottom has a net capacitive reactance. So now let's look at this other antenna. So you can see it also has a pretty good SWR of 1.4. It's under 2, which is good. Look at the Smith chart and it looks a little different. So we took two antennas that had to be trimmed to different lengths in order to match them as best as possible to a 50 ohm impedance. This is a good example of how the transmission line can affect the performance of your antenna. Pretty much everything near your antenna can affect the impedance and degrade the performance, so it's a good idea to do the final tuning of your antenna in the environment that it will be used in. Here you'll see that this clear vinyl tubing negatively affects the performance of this antenna by increasing its SWR from 1.3 to about 2.7. Antenna designers take this into account and tune the antenna inside the enclosure it will be used in, like this dipole you saw earlier. So you can see that the SWR is about 1.1 and it's about dead center on the Smith chart. So if we take this protective enclosure off the dipole antenna, you'll see that it changes the SWR from about 1.1 to about 1.5. Now it's still pretty good either way, but you can tell that the designer had the enclosure in mind when tuning it. So now the question, why quarter wavelength and not whole wavelength? And I'll show you. So we take this copper wire and we cut it to one wavelength. Actually it's cut a little longer so that exactly one wavelength is sticking out of the center conductor of the connector. So you can see that the SWR is about 3.6, even though it's a resonant antenna. So you could use this antenna, but you'd have to use a Balun to match the impedances from 14 ohms of the antenna to 50 ohm transmitter. Another parameter that changes when going beyond quarter wavelength for a monopole antenna is that the radiation pattern changes. Quarter wavelength vertical monopole antenna mounted above a good ground plane gives us a nice uniform omnidirectional radiation pattern like this. When we go above a quarter wavelength, the radiation pattern becomes less and less omnidirectional. For your application, this may be fine because the benefit of a longer antenna is that it has more area for reception and can transmit and receive above surrounding objects. Many monopole antennas that are mounted on cars are about 5/8 of a wavelength long for this very reason. Just like the impedance, the radiation pattern of an antenna is pretty much affected by everything that's nearby. In the last video I said that an antenna system is a complex RLC network. The resistance is composed of R loss and the radiation resistance of the antenna elements. R loss is from the actual resistance of the conductors, and power dissipated in this manner is lost as heat. This value is not stable like in a DC circuit and varies with frequency, so you can't measure this with a multimeter. The impedance is in ohms and is composed of the total resistance plus the inductive reactance subtracted by the capacitive reactance. Remember that the antenna is said to be resonant when the inductive reactance and the capacitive reactance cancel each other out. Now, an antenna does not need to be resonant in order to be a good antenna, and it's not always practical either. For example, a quarter wavelength monopole antenna for a 60 kHz transmitter would be well over a kilometer long. In the next video, we'll discuss dipole antennas and go into what the gain of an antenna is and how it's measured. See you next time. Hey guys, so thanks to Keysight, I'll be doing an introduction to antenna design with their FieldFox unit. I'll be covering a variety of different antennas and what they're typically used for, as well as the pros and cons of the designs. In this video, I'll go over some of the terminology we'll be using in the series. The antenna system is often described as a complex RLC network consisting of a resistive component, an inductive reactance, and a capacitive reactance. At specific frequencies, the inductive reactance and capacitive reactance cancel each other out and we're left with a purely resistive antenna. At these frequencies, the antenna is said to be resonant. In order to minimize power losses, we need to match the antenna's impedance to the device's impedance. The majority of transmitters and transceivers have an output impedance of 50 ohms. Now, you might be wondering why 50 ohms, and there's a good reason for it. The reason for the popularity of the 50 ohm standard is because in the late 1920s, researchers from Bell Labs found that an impedance of 30 ohms was best suited for power handling, and an impedance of 75 ohms was best in terms of the signal quality. The 50 ohm standard was decided on because it's a great balance between power handling and signal quality. To see a practical example of this across a frequency span, we can look at a Smith chart. A Smith chart is used to plot the impedance of an antenna throughout a defined frequency range. So what we're looking at is everything in the top hemisphere has a net capacitive reactance, and everything in the bottom hemisphere has a net inductive reactance. This center line represents the resistive component of the impedance, and everything that crosses this line represents the resonant frequencies of the antenna. Okay, so here I have a simple 5.8 gigahertz antenna, and I have the Smith chart plotting from 5 gigahertz all the way to 7 gigahertz. So because the transmitter is expecting a 50 ohm load, we want to be as close to this 50 mark and as close to this line as possible. Remember, I said that this line here, everything that crosses this line, is a resonant frequency of the antenna. So we hook it up, and we see I have a marker set to 5.8 gigahertz, and it's very close to the line, and it's very close to the 50 mark, so this wouldn't require any matching. Now you see that this antenna has several resonant frequencies across the span, and so those would work, but it would require matching to 50 ohms because the transmitter is expecting 50 ohms. So this antenna has another resonant frequency of 6.5 gigahertz, and the impedance is roughly 144 ohms. So if the transmitter is expecting a 50 ohm load and we give it a 144 ohm antenna, it's really not going to radiate very well. It'll work, and it might work for your application, but if we want the best antenna possible, we want to match our transmitter to our antenna and get as close to the 50 mark as possible. Another graph we can look at is the Vswr graph. VSWR stands for voltage standing wave ratio, and we often just shorten it to SWR. The SWR is determined by the amount of the transmitted signal that is reflected back to the transmitter and is essentially a measure of how well an antenna is matched to its source impedance. A perfect match is 1 to 1, but a ratio of 2 to 1 is what most manufacturers aim for and is often how they list the bandwidth of their antenna. An antenna with an SWR of 2 to 1 at a given frequency will radiate a little under 90% of the power that is fed into the antenna and reflect back the rest. SWR is really important when analyzing an antenna, but just because an antenna has a low SWR doesn't mean it's a good antenna. For example, if we take the SMA connector and solder a 50 ohm resistor between the center conductor and the outer casing and connect it to the network analyzer, we can see that it has a SWR under 2 from DC all the way to 3 gigahertz. But it would make an awful antenna because it doesn't really have any radiating elements. Another important factor when analyzing an antenna system is balanced and unbalanced cables. When we have two identical conductors carrying current in opposite directions, the fields they create cancel each other out. If the two conductors are not identical, like coax cable, you're left with a feed line that radiates some of the transmitter's power. Even though coax cable is not a balanced cable, it only becomes a big issue if you're running long lengths of cable. In that case, you'll want to use what's called a Balun. The name Balun comes from the device's function, which is to adapt a balanced line to an unbalanced line. You can also find baluns that will not only balance your feed line, but also transform impedances to help with matching your antenna to its source impedance. In this series, I won't really be going into feed lines because I'd like to just focus on the antenna designs themselves. Hope you liked the video, and I'll see you next time.